So today we're going to do some calculations for Module 3, and I think you'll find that the calculations in this module are very simple compared to the last two modules. So let's start off with the problem. We're given the diameter and the length of a wire. It's got 1 millimeter diameter. So D equals 1 millimeter. And it's 2 meters long. So L is equal to 2.0 meters. And the resistance, which is R, is 50 milliohms. 50 times 10 to the minus 3 ohms, to put it in standard units. And they want to know what's the resistivity of the metal. Resistivity is rho. So we do the same thing that we do for any kind of word problem in math or physics. We pull out everything that we're given in the problem, we give it its proper label, and then we look at the equations, which are all at the bottom, to figure out which one we want to use. So I want to find the resistivity. There's only one equation at the bottom that has resistivity in it, so that makes it simple to choose which equation. We're just going to use that middle equation. So I want to find rho, and so I've got R equals rho L over A. I want to rearrange that to get rho, so I'm going to get rid of the A, I'm going to multiply it up to the other side and then divide by L. Okay, so do I know the things in the equation? Well, I've got my R and I've got my L. Those were given directly. Do I know the area? Well, I know the diameter, and I know that the area of a circle is pi r squared. So area is pi r squared. And this equation would not be given on an equation sheet for a test. It's sort of basic knowledge that I would anticipate that you would already know. And what's the radius? The radius is half the diameter. Okay, so the diameter is 1 millimeter, or 1 times 10 to the minus 3 meters. And so the radius is the diameter over 2, so it's going to be 0.5 times 10 to the minus 3 meters. So let's calculate the area then. It's going to be a really small number, isn't it? So it's going to be pi times 0.5 times 10 to the minus 3 squared, and I get 7.85 times 10 to the minus 7, and the area has units of meters squared. Okay, so now I know everything. Now I'm just going to plug them back into the equation for the resistivity. So the resistivity is R, which is 50 times 10 to the minus 3, times the area, 7.85 times 10 to the minus 7. So I'm multiplying two small numbers times each other, so I anticipate I'm going to get a small number. And then divided by the length, which is 2. If I put all that into my calculator, I get 1.96 times 10 to the minus 8. And the units for resistivity is ohms times meters. Okay, so that's the resistivity of the material. Okay, let's do another one using some of the other equations. So I've got 120 volts is applied to a 14 ohm space heater. So again, read the numbers and figure out what the variables are. So V is equal to 120 volts. 14 ohms. Ohms is resistance, so R is equal to 14 ohms. And in part A, it says, what is the power? All right, so I want to find the power, so I can't use the first equation. I can't use the middle equation. I got to use this end equation. In this end equation, I've got 3 equations ganged together. And remember, what that means is you choose the equation that's relevant to what you're given in the problem. So in the problem, we're given the V and the R. So we're going to use the last part. We're going to use P equals V squared over R. If I'd been given I and R, I would have used the middle one. If I'd been given I and V, I would have used the first one. All right, so I've got 120 squared divided by 14, and I get 1029 And the units for power, remember from Physics 1, is watts. Okay, so there's my power. Part B says, if you're charged 5 cents per kilowatt hour, how much does it cost to run for 5 hours? So let's think about that. So I've got 5 cents per kilowatt hour. I want to find the total cost. All right, so the cost is going to be equal to the cost per kilowatt hour times the number of kilowatt hours, right? If I go to the store and I buy 10 apples and each apple costs 50 cents, then the total cost is going to be 10 apples times the cost per apple of 50 cents will give me $5. Okay, so we know the cost per kilowatt hour is 5 cents. So the question is, how many kilowatt hours do we have? So the number of kilowatt hours, well, it's just the number of kilowatts times the number of hours. Okay, so we have 1,029 watts. Remember, 1 kilowatt is 1,000 watts. So if I divide that by 1,000, I'm going to get 1.029 kilowatts. Okay, so that's my number of kilowatts. And the number of hours is 5. So if I put that all together, the total cost on my electric bill is going to be cost per kilowatt hour, 5 cents per kilowatt hour, times 1.029 kilowatts times 5 hours. And if you look at the units, you can see the kilowatts cancel out from the numerator denominator, the hours cancel out, and I'm left with just cents, which is what I should have if I'm doing a price. All right, so I've got 5 times 1.029 times 5. I'm going to get just 26 cents. All right, so it didn't cost me very much to run that heater overnight. All right, so the next topic in the chapter is alternating current. So we've been assuming so far that we just hook it up to a battery where we have a constant current and a constant voltage as a function of time. But when we plug something into the wall, what we get instead is a current that goes up and down with time 60 times a second in this country. So direct current, DC, is a battery where you've got steady flow in one direction. Alternating current varies like a sine wave, so sinusoidally, with a frequency f, and that's what comes from the wall, from a power plant or from your electric generator if you run one during a hurricane. So both the current and the voltage vary sinusoidally with time, and so we can have an equation where V is equal to V0, the maximum, times sine omega t, and I equals I0 times sine omega t. Remember omega, back from Physics 1, is 2 pi times the frequency, so F is the frequency in hertz. And in this country, when you plug into the wall, we've got 60 hertz. And omega was the angular frequency in radians per second. Okay, so the V0 and I0 are the maximum voltage and the maximum current, and omega and F give you the frequency. So what's the power? Well, remember we said power was current times voltage, or I squared R, or V squared over R. So if I look at the equation, power equals I squared R, and now instead, for the current, I put in that I equals I0 sine omega t. If I square that current, I'm going to get I0 squared sine squared omega t. So my power now, instead of being constant, goes like a sine squared function, which is shown in the graph below. So it's always positive. The power is going to have a maximum value of I0 squared over R. And to get the average value, we have to add up all the area underneath those sine waves and then divide by the time. And if we do that, the mean, so remember back in physics 1 when we had a mean, we wrote a bar over the top, like for average velocity, we wrote v bar. Same thing here. So this bar over the top just means it's the average power. The average power is half of I0 squared over r. The average of a sine squared function turns out to just be 1/2. And so the average power is 1/2 I0 squared over r, or if we did it with the fact that power is v squared over r, we would get that it's half of v0 squared over r. So the average power is just half of the maximum power. So since, if I go back, the average current, if I average all the current, I would have equal amounts above and below and I would get 0. Same thing for the voltage because they vary sinusoidally. So the average current and the average voltage are 0. So instead of averaging the sine wave, we average the square, which makes everything positive, and then we take the square root. Okay, so we average the square and then we take the square root. And so that's what you see in these symbols down below here. So we take the average of the square and then take the square root. And so we're taking the root of the mean, which means average, of the square. So that's called a root mean square, or RMS value. So when you have a voltmeter or an ammeter and you hook it up to an alternating current source, they don't read the average. What they read is the root mean square value, which is the peak value divided by root 2, and 1 over root 2 is 0.707. So the RMS value of current is the maximum current times 0.707, and the RMS value of the voltage is the maximum voltage times 0.707. So let's do a couple of quick calculations there. So if I've got an AC generator that has a maximum voltage of 24 volts, and it's attached to a 265 ohm load. So again, let's take out our numbers from the problem and assign symbols to them. So I've got V and I've got R. So V equals 24. And it says that's the maximum voltage, so I'm going to put a V0. That's the peak value of the voltage. The R is 265 ohms. I want to find VRMS, IRMS, and the average power. So VRMS is V0 times 0.707. So that's easy. I've got my V0. So VRMS is V0 times 0.707. So that's 24 times 0.707, or 24 divided by root 2. And I get 17 volts. All right, so that's my VRMS. What's my IRMS? Well, I can find that my I0 and my V0 are related to each other. Okay, so remember V equals IR, Ohm's law. So V0 is also equal to I0 times R. And I know my V0 and I know my R. So I0 is just going to be V0 over R. Okay, so to get my IRMS is I0 over root 2. I can just do V0 over R divided by root 2. Okay, so 24 over root 2, or times 0.707, whichever you want to do, times 265. And I get 0.0640 amps. Or I could use the fact that IRMS is equal to just VRMS over R, since VRMS equals IRMS times R. So the voltage at any point is equal to the current at that point times R. And if you do that, you're going to get the same number. All right, so I've done VRMS, I've done IRMS. What's the average power? Well, the average power was equal to 1/2 of I0 squared R, or it was 1/2 of V0 squared over R. So I could use the first one, or I could use the second one. And of course, it would also be 1/2 of I0 R0, sorry, I0 V0. We have those three equations that are equivalent. Which one am I going to use? I'm going to use the middle one here. Why am I going to use that? Because the problem gave me V0 and R, and so then I don't have to rely on whether I did my calculation of I0 correctly. So I could have done it anyway. I want to, but I'm going to use the one where I'm going to use the numbers that were given in the problem, because then I'm less likely to mess up. So average power is 1/2 of V0 squared, 25 squared over 265. If I do that, I get 2.18 watts. Okay, so hopefully you found these equations a little bit easier to work with. Let's do one more where we don't actually use an equation. So how many electrons pass through a wire in 4.5 seconds if the current is 0.22 amps? Okay, what does that mean? Well, remember, current is charge per time. Okay, so I'm told the current and I'm told the time, so I can get the total charge passing through the wire in that time is going to be the current times the time. So it's going to be 0.22 times 4.5. And so I'm going to get 0.99 coulombs. So almost 1 coulomb of charge passes through the wire. Okay, so now the question is, how can I figure out how many electrons pass through the wire? Well, what do I know about an electron? Well, I know the electron has a charge of minus 1.6 times 10 to the minus 19 coulombs. I'm going to ignore the minus right now because I'm just counting the magnitude. Okay, so each electron has a charge of 1.6 times 10 to the minus 19 coulombs, and I've got a total of 0.99 coulombs. So how am I going to find it? I don't have an equation. Okay, well, let me ask you a question. Let's say that you had a party and you told every student that you're raising canned food for a food drive, and that each student for entrance has to bring 2 cans of food. And you don't count how many students who come, but at the end of the party you count how many cans, and let's say you have 100 cans of food. So you say, okay, I have 100 cans of food, each student brought 2 cans. How do you figure out how many students came? What you do is you divide the number of cans by the number of cans that each student brought. So you do 100 divided by 2, and you'd get 50 students came to your party. So we're going to do the same thing here. I've got 0.99 coulombs of charge. That's my total that was brought by the students. Each electron is bringing 1.6 times 10 to the minus 19 coulombs. So that's like each student bringing 2 cans. So how am I going to do it? The number of electrons is just going to be the total charge divided by the charge per electron. Okay, so 0.99 coulombs divided by 1.6 times 10 to the minus 19. And again, a reminder, when you do this, make sure you put your brackets on your calculator or use the EE function instead of times 10 to the 19. All right, so if I put that in, I'm going to get a really big number of electrons, 6.2 times 10 to the 18 electrons. Okay, so that's about every different kind of problem that I can think of that you could be asked to do for this chapter. So let me give you a problem for your active learning problem. So here you've got a piece of wire. I told you it's iron. It is 6 meters long, has a diameter of 0.1 centimeter. I give you the resistivity of the iron, and I ask you to find the resistance of the wire. And then if you hook it up to a battery, what current will flow, how much power is used, and then how much will it cost to run it for 5 hours at a cost of 7 cents per kilowatt hour. So you're going to do equations and calculations similar to what I did. Again, remember, put everything into meters and hours, meters, seconds, ohms for doing your calculations. When you do the last one where you're doing kilowatt hours, you need to put your power from part C into kilowatts and the time into hours to get the correct answer.